Coming to problem number 11. A vessel displaces 14,500 metric tons if floating in salt water up to her winter load line. If she is in a dock water of RD 1.010 with her winter load line on the surface of the water, find how much cargo she can load so that she would float at her winter load line in salt water. So let us see the explanation to the problem. Given in the problem, the data is displacement in salt water at the winter load line is equal to 14,500 metric tons. And she is floating now in dock water 1.010. The draft in salt water is equal to the draft in dock water. We have to find how much cargo she can load so that she would float at her winter load line in salt water. Now consider the drawing on the right hand side. We have the load lines, we have the deck line. Now I would like to advise all of you that the lines that you see, the horizontal lines that you see that I am highlighting, and also the deck line, they are basis the top of their respective load lines. Each load line and deck line being 25 millimeters thick. So these lines all represent the top of their respective load lines. Now, having said that, let us see what it wants. Her winter load line on the surface of the water. The winter load line is on the surface of the water, and the water is dock water 1.010. Her displacement in salt water is 14,500. She is floating at her winter load line in dock water of 1.010. So when she goes into the salt water, she is going from water of lesser relative density to water of higher relative density. Therefore, the ship will rise and she will float at this. The water line will come at this point, this line that I have highlighted now, which means that you have underloaded the ship. By how much? That is what we have to find out. And to load her correctly, perfectly, so that when she goes into the salt water, her winter load line should be, the top of the winter load line should be at the water line. It is always that the load lines are for salt water. Thus, we have to calculate something called dock water allowance. Or, in other words, since it is not mentioned in this problem that it is a ship, we can safely assume it to be a box-shaped vessel and work according to this formula, which we have learnt earlier. How do we know that she is not a ship but is a box-shaped vessel? Her TPC and her freshwater allowance is not given in this problem. Thus, we have displacement in salt water equal to length into breadth into draft in salt water multiplied by the relative density of salt water, and displacement in dock water is equal to length into breadth into draft in dock water multiplied by the relative density of dock water. We know that the drafts in dock water and salt water are the same. Therefore, displacement in dock water divided by length into breadth into relative density of dock water will be equal to displacement in salt water divided by length into breadth into relative density of salt water. From this we find, after we cancel out length into breadth on both sides, Displacement in dock water is equal to 14,500 divided by 1.025 multiplied by 1.010, giving us a value of 14,287.8 metric tons. Therefore, the cargo to load will be equal to 14,500 minus 14,287.8 equal to 212.2 metric tons. Problem 12. A vessel of 12,000 metric tons displacement arrives at the mouth of a river, drawing 10 meters in salt water. How much cargo must she discharge so that her draft in an upriver port of relative density 1.012 would be 10 meters? So here once again we note that she comes at the mouth of the river from the sea and she is at a draft of 10 meters in salt water. She has to go upriver where the relative density of the water is 1.012 and still maintain her draft at 10 meters. That can only be possible if she discharges some cargo at anchorage so that when she goes upriver, she will sink automatically to a draft of 10 meters. If she does not do that, the consequences are that she will run aground somewhere in the river because that is the minimum required draft, which is 10 meters. So now let us assume that she has come from the sea in salt water and she has dropped anchor outside the river. She is floating in salt water. Refer to the drawing on the top on the right hand side. She has come from the sea and is floating at her saltwater draft of 10 meters. Now, if she were to do nothing and just proceed up the river, what would happen? Her draft would increase because she is going from water of higher relative density to a water of lesser relative density. That means her draft would increase, let us say, assume until this level. And since the draft has increased, she is overloaded, she can run aground, and there will be other consequences. Thus, when she goes into water of relative density 1.012 from salt water, she must be at a lesser draft in salt water to begin with. And to do that, for that to happen, she has to discharge some cargo at the anchorage. Thus, her draft must reduce to this level. Look at the picture at the bottom now. When she is at anchorage and she is discharging cargo, she must arrive, stop discharging at this draft. What is that draft? How much it is, that can be calculated. So when she goes from this draft into the dock water of 1.012, the ship will sink and she will now settle down at this draft of 10 meters in 1.012. Once again, her freshwater allowance and TPC is not given to us in the problem, so we can work this out. We have to work this out using the length breadth draft method. So let's start. Let's see. The data given to us in the problem is this. Her displacement in salt water is 12,000 metric tons. Drafts in salt water and dock water are going to be the same, 10 meters. Relative density of salt water we know is 1.025 and relative density of the dock water upriver is 1.012. We know the formulas for displacement: length into breadth into draft in salt water multiplied by relative density of salt water, and displacement in dock water is equal to length into breadth into draft in dock water multiplied by relative density of dock water. Given to us, the two drafts are the same. Therefore, displacement in dock water divided by length into breadth into relative density of dock water is equal to displacement in salt water divided by length into breadth into the relative density of salt water. When we substitute all the values after cancelling out length and breadth on both sides, we get displacement in dock water equal to 11,847.8 metric tons. We know her displacement on arrival was 12,000 and she has to reduce her displacement to 11,847.8. Therefore, she has to discharge 152.2 metric tons. After she discharges 152.2 metric tons, her water line, when she is floating in salt water, will be at this level. And when she goes into dock water of 1.012, the water line will automatically settle at the bottom of 10-meter draft. Problem 14. A vessel floating at 7.8 meter draft in dock water of RD 1.010. TPC is 18 and freshwater allowance is 250 millimeters. The maximum permissible draft in salt water is 8 meters. Find the deadweight available. Now we know that to calculate deadweight available, you need two displacements. First displacement that you need is the displacement at your maximum permissible draft in salt water at 8 meters. Another displacement that you will need is at 7.8 meter draft in dock water of 1.010. The difference between these two displacements will give you the deadweight available. But in this problem, we cannot work with this method because the two displacements are not given and also cannot be calculated independently. We have to think of another method. And that other method is using TPC and freshwater allowance and the two drafts. So let us see how to go about solving this problem. Given to us in the problem is this data, and we are going to use this on the next slide, part of this data on the next slide. The first thing, ideal thing that you must do is draw what is required. Draw what is given, and from that it will be easy to compute, to calculate what is required. So taking the picture on your left hand side, we have the draft marks going from 7.4 meters to 8.2 meters. It is given to us that the ship is floating at a draft of 7.8 meters in dock water of 1.010. Now, if you were to do nothing, if the ship was to do nothing and she was to go into salt water, her draft will reduce and it will settle down at this green line in salt water. How much will it reduce? That we have to calculate. And that how much it will reduce by is called dock water allowance. Now, coming to the drawing on the right hand side, we know that our draft marks, the height of each draft mark is 100 millimeters and the distance between the two draft marks is also equal to 100 millimeters. We have calculated, as we will see in the next slide, our dock water allowance to be equal to 150 millimeters. Thus, if you were to do nothing, if this ship was to do nothing, this draft at 7.8 meters will reduce by 150 millimeters because from water of lesser relative density to salt water, which is water of greater relative density, the draft will reduce and it will settle at this line, the green dashed line, lower by 150 millimeters. That is at 7.65 meter draft. We have to calculate the dead weight available. She will be at 7.65 meters and her maximum permissible draft is 8 meters. Thus we have a difference of 10 meters plus, I'm sorry, not 10 meters, 10 centimeters plus another 10 centimeters plus another dock water allowance 15 centimeters, giving us a total of 350 millimeters or 35 centimeters. Now, TPC given to us in the problem is 18 metric tons per centimeter. Always remember, even though it is not mentioned as to which water this TPC is referenced with, it is always salt water. Thus, the TPC of 18 meters in this problem is with reference to salt water and it has to be converted to TPC in dock water. The easiest way to go about doing this is you divide this TPC of 18 by a relative density of salt water 1.025 and you multiply it by the relative density of the dock water given to us to be 1.010. So it works out to 18 divided by 1.025 multiplied by 1.010. It works out to 17.74 metric tons per centimeter. So let us go to the solution now. This data is given to us in the problem. We have to find dock water allowance and that is equal to freshwater allowance multiplied by the difference of two relative densities divided by 0.025, giving us a value of 150 millimeters, which I showed you in the right hand side drawing. When the vessel enters salt water, she will rise and the draft will reduce by 150 millimeters or 15 centimeters or 0.150 meters. Hence the actual draft will be 7.8 minus 0.15 equal to 7.650 meters. Sinkage available will be maximum permissible draft in salt water, which is 8 meters, minus the present draft in salt water, which is 7.65 meters, is equal to 35 centimeters or 0.350 meters. Another way to look at it is, as I explained earlier, you have 100 millimeters plus another 100 millimeters, 200 millimeters, that is equal to plus dock water allowance 150 millimeters, that is a total of 350 millimeters or 35 centimeters. Now, after converting, we have to convert the TPC from salt water to dock water, and as I explained earlier, TPC in dock water is equal to TPC in salt water divided by relative density of salt water multiplied by the relative density of dock water, giving us 17.74 metric tons per centimeter. Therefore, the dead weight will be equal to sinkage multiplied by TPC. Sinkage we have seen in centimeters equal to 35 and TPC is 17.74 metric tons per centimeter. Therefore, dead weight available is equal to 620.9 metric tons.